This is Pre-Calculus section 9.4 on parametrics, and this is our parametric lab. And I'm skipping down to problem number 2. Here are the directions for this problem, and I have everything already worked out. The way we're coming up with these parametrics is to look at what point you're starting with, and then what is the change. For instance, this is going from point A to point B. It's starting at 0, 0, and it's going right by 2 and up by 5. So we attach that to the variable of t for time, and then we can do that x equals 0 plus 2t, get that equation. Also, y equals 0 plus 5t to get that equation. And that's going to go in as our first parametric. From B to C, it's starting at 2 comma 5. And then from 2 comma 5 to 4 comma 0, it's going right 2, it's going down by 5. So this is kind of like a slope, right 2, down 5. And so then from here we have x equals 2 plus 2t, and y equals 5 plus negative 5t. So that's going to be our second parametric. We either do the same thing, c to d, d to e, e to a. So we get all these parametrics, always with the initial point plus the change times t. So now if I go back to the calculator, I have all these entered in as y equals, and under window, I want to make sure that the t max stops at 1. I only want this to happen for 1 second, in other words. The t step determines how fast it is. If I have t step be equal to 1, I hit graph, it's going to go really fast, and I can't quite keep up with it. So I'll go back to window, change that to something smaller, like 0.02 maybe, hit graph, and that slows it down, and I can see each one of those different sections being drawn out. Next, we want to make sure that we switch the mode on the calculator to simultaneous. So I'll hit the mode button, and normally we have this in sequential order. I'll scroll down and change it to simultaneous, and we'll see what that looks like once we get into the graphing part of this one. Ken is standing at this point trying to shoot clay pigeons. The clay pigeon's path is represented by this. We want to, in part A, graph the first 4 seconds of the clay pigeon's path. So I'm going to have time 0, 1, 2, 3, 4 seconds. Plug these t values into that equation to come up with the location. In other words, at 2 seconds, it's over 31, up 14. At 3 seconds, we plug 3 into t to both of those to get the x and y value, and we have that location. So there is the graph of the clay pigeon. It's nice and linear. Part B says, give the parametric equation that Ken should use to hit the clay pigeons at 2 seconds. Ken is standing at 0, comma 1. So we have our x comma y equals 0, 1, that's the initial, plus going from 0, 1 to the point 31, comma 14, because that's where the clay pigeon is at 2 seconds, means you're going right by 31 and up by 13 times t, but we're doing that in 2 seconds, so then we have to divide that by 2, otherwise it's going to get there too quickly. And from there we can get our two equations. X equals 31 halves t, and y equals 1 plus 13 halves. So we have those equations, and I'll go to the calculator, enter them in so we can see what this actually looks like. Both of these equations are entered into the graphing calculator now, and we want to see what this looks like. If I hit graph, that's what's going to show up, and that doesn't really do a whole lot. We're going to go to the window, and we need to think about this. First of all, for the t part, t min is 0, that's time 0. If we want them to hit at 2 seconds, we have to change our t max to 2. T step will keep something small again so we can see that. And then we have the x values. Now, as I think about the graph for this one, the x value is going to go maybe back to here, so I can have my -1. And then the x max, well, since they're going to hit at an x value of 31, I want to be a little bit to the right of that. So x min will put in -2, and x max will put in maybe 40, so we can see a decent window on that one. X scale doesn't really matter. And then for the y min, we'll have that one go down to 0. That's how low it's going to go. And then they're going to hit at a y value at a height of 14. So we want our y value to be something a little bigger than that, maybe like 18. Hit enter, and now we'll go to the graph. It's graphing both of them simultaneously, and we can see they collide right at that point. You can see this chart here at 2 seconds. They're both at the point 31, comma 14, so I know I did that one correctly then. Here's the last problem. We have an object that's traveling in this direction. We have the parametric x equals this, y equals that. And for this one, I mentioned that you need to put this into degree mode because we're finding angle measurements and I want to be able to use degrees instead of radians. It'll be a little easier for us. Here's the window setup to make it work. And we are standing at the point -5, -10. We want to hit it at 90 seconds. Very convenient because we can find the sine of 90 and the cosine of 90. So at 90 seconds, we plug it into the parametric to see that the object is located at the point 16, 21. Plug the 90 in here, plug the 90 in there, and boom, we have the location. So at 90 seconds, we want to go from our point, which is -5, -10, to the point 16, 21. So x equals -5 plus, then the change in x, it's increasing by 21. We have to do 21 over 90 because we want to happen in 90 seconds, not just in 1 second. And the y is starting at -10. It's increasing by 31, so it's -10 plus 31 over 90t because we want it to happen in 90 seconds. So if we enter in these parametrics, we'll see the orbit of the object we're trying to hit. Then we'll see the object we are throwing at it, hitting it at 90 seconds. And for this one, you might want to speed up your t step to something a little faster. Otherwise, it's going to take a long time to see what happens in 90 seconds. Then you can see these two objects colliding.